Now, one thing we have done to simplify our whole calculations, and that is we have taken equal spacings. The energy levels were all equal, and therefore, we could actually manage to count using the partition thing, because we use partition 7 into 9, knowing very well that the sum up will give me 9 when I am partitioning 9. Sum has to be 9. We knew that, and then since integer goes in an integral manner, like 1 plus 2 plus 3, 1 plus 1 plus 1, like that, 1 2 3. Similarly, energy levels were like 1 2 3. However, if energy levels are all unequal, then we cannot do the same thing. For example, we have a very simple system like particle in a box, and that does not give us unequal energy spacings. As you know that energy levels keep on increasing. So, this is taken from Atkins' physical chemistry book, this picture. So, as you know that when the energy levels increase, the difference keep on increasing. So, if you use this particle in a box concept, it will be very difficult to do that. The realistic system that we talked about for equal energy spacing is harmonic oscillator, where the energy levels are equally spaced. However, it is not true when it is actually a realistic system. Harmonic oscillator is solved by using a parabolic half kx square parabolic potential, and that is how we get that. However, if it is a realistic system where let us say a bond is connected by an atom is connected by 2 bonds simultaneously, so there will be an combined effect of motions of both the atoms. It will be no longer a very simple harmonic oscillator anymore, and therefore, no longer equal spacings. So, in realistic situations, we may not get equal spacings of energy levels and calculate the statistics the way we have done that till now. So, therefore, we need a more robust, more a rigorous approach to calculate these statistics. So, as is mentioned here, and in fact, we have used, in order to calculate for Maxwell-Boltzmann, we have used all possible microstates, right. When you calculated the statistics of 5 units of energy in 4 particles or 7 units of energy 9 particles, we used all possible microstates and calculated that how many microstates will be there for the particle having ith energy level. However, we have mentioned before that we do not need that. We only need one distribution, which is the most probable distribution. We showed that when the number of particles goes very high, for example, we showed up to 10 to the power 8 or 9, that it is really narrow. It falls off within. So, we have shown the calculation, right, that for 10 to the power 23 particle with 0.000000002%, the distribution will decay to 0, which means that most probable distribution is enough to give us the all possible microstates, and therefore, to give us an estimate of entropy. So, that means we have to know how to calculate most probable distributions irrespective of whatever the energy levels are. We do not have to care about the energy levels. Irrespective of the energy levels, energy spacing, we should be able to get the distributions of particles in the most probable distribution. Will that follow an exponential distribution like this? Let us see that. How do you calculate the MPD for an arbitrary system? So, we will see that MPD for a general system, to calculate that the Boltzmann will actually come to a rescue, Boltzmann distribution, and we are going to maximize the W under the constraints of total energy and total number of particles, and that will give us, as you have seen, the Maxwell-Boltzmann distribution or an exponential distribution. So, we are going to do the derivation. However, this derivation is not actually a part of this syllabus. This you can take as an additional thing for the completeness of this particular course. You can also find the derivation in the physical chemistry book of Atkins. So, this derivation is just for the completeness of the course rather than the part of the lecture. So, for Maxwell-Boltzmann distribution, we know that W is n factorial by n1 factorial, n2 factorial, n3 factorial, etc., which can be written as n factorial by product of n I factorial, and that product runs over so many i's, we do not know how many i's. So, which you can see that in that case that W is a function of ni's, because that will give us the W if I know the ni. So, W now becomes function of ni, and we have two constraints. One constraint is that the total number of particles sum over I is n, which is a fixed quantity, and total energy, which is product of ni ei, is some value E, that is also fixed. So, if we maximize this particular W under the constraints of this and this, then we can see what kind of W we are going to get, but whatever W we are going to get, that will be the most probable distribution, W for the most probable distribution. And as you have seen that is enough for getting the statistics. So, that most probable distribution will be enough. Note here is that we have not specified how the energy spacings need to be, that is not required, and so we do not need any equal spacings here anymore. We only need that the total energy has to be conserved. Okay, and that we know for systems will be conserved. For an isolated system, the total energy will be conserved, and also for other systems as well, but we are not going to discuss that right now. So, now let us see how we can maximize the W. So, in order to do that, it is much easier to work with ln W than W, and we know ln W will be ln of n factorial by product of I ni factorial, which is ln n factorial minus ln of product of ni factorial, which is ln n factorial minus. So, product becomes sum in case of ln, and it will be ln ni factorial. So, which means now our W ln W is also a function of ni. So, now we can write then, so all variations of ni only will give us the maximum W. For example, we have seen that for two level systems, if ni is 1, n1 is 1 and n2 is n minus 1, it gives us one distribution. If n1 is 2 and n2 is n minus 2, it gives another distribution, and the most probable distribution is only when ni or n1 becomes n by 2. So, that means this W is basically a function of that time n1. Here there are multiple values of n1, n2 and n3s are there. So, we are trying to maximize the W with respect to some arbitrary I, and I is arbitrary because I can be put as 1 or 2 or 3 whatever. So, we can write the differential amount of W ln W as you have seen for any differential quantity when it is a function of multiple variables, can be written as del ln W by del ni d ni. Now, since there is a sum over that, we can put a sum I. In order to satisfy the constraints, there is a method called Lagrange method of undeterminate multiplier, which means that you have to multiply by some constants to those constraints, and we can maximize the quantity. So, now if we write down the quantity that need to be maximized, now is that d ln W is sum over I del ln W by del ni d ni plus alpha d ni. Alpha is just one of the constraints, undeterminate constraints, and minus beta is another constraints where we satisfy the condition of total energy, and that needs to be equal to 0. As you know that for maximum minimum function, the differentiation has to be done, and that has to be equated to 0, because that gives us the value of maximum and minimum. So, now when you write them together, del ln W by del ni plus alpha minus beta ei sum over d ni gives me 0, which means this quantity inside has to be 0. So, del ln W by del ni plus alpha minus beta ei is equal to 0. What is ln W? ln W is as you know, ln w is written here somewhere. Yeah, no, I have not. Yeah, ln w is written here, equation 1, ln n factorial minus sum over ln ni factorial. So, del ln w by del ni will be del ln ni n factorial by del ni minus sum over I del ln ni factorial by del ni. Let us call it 1 and 2. So, now let us do the 1 and 2 separately. So, 1 is del ln n factorial by del ni. Now, we know that using Stirling's approximation that ln n factorial is n ln n minus n, and the n itself is sum over ni's. So, let us write that del ni of n ln n minus n, let us write that as sum over ni ln n minus sum over ni. Now, once I do that, I have the sum and then I do del ni of ni ln n minus sum over del ni of ni. Now, this is a product sum. So, the first term will be ln n, and as you see the sum will go away, because only one of the term will survive, only one of the ni will survive. You can think of that you are differentiating with respect to n 1, and then you see that this is a sum of n 1 plus n 2 plus n 3, this one, and therefore, only one term will survive and you are going to get only 1. So, ln n will survive, plus now I have ni differentiation of ln n, which means if I differentiate with respect to ln n, let us do that in the next step. Left hand side I will still get 1 because only one term will survive. So, ln n plus ni. Now, when you differentiate with respect to ln n, what you are going to get is you are going to get 1 by n ni into 1 by n. This sum is still there in this particular case, and differentiation of sum of ni by ni minus 1. So, then it is ln n. Now, this term is going to be 1 and sum of ni by n is going to be 1 minus 1, and you are going to get ln n. Now, let us do the second term. What was the second term? Let us see. Second term was this particular term, sum over I del ln ni factorial by del ni. Is that the case? Let me see. Del ni factorial by del ni, yes, that is the case. So, then sum over I del ni ln ni n I ln ni minus ni. Again, in this case you have ni, ln ni will be 1 by ni, and the sum will go away because there is only one term that is going to survive, and ln ni. There is also the sum will go away because only one term is going to survive, and in this case the second term will be just 1. So, here this cancels, giving me 1 plus ln ni minus 1. So, they cancel and I get ln ni. So, 1 minus 2 is going to give me ln n minus ln ni, which is ln n by ni. Now, when I combine that with the other terms coming from this equation, now going back to this equation, let us call it equation 1. Now, plugging that into equation 1, we got this one as ln n by Ni plus alpha minus beta Ei. So then ln n by Ni plus alpha minus beta Ei is going to be 0, which means minus ln Ni by n plus alpha minus beta Ei is going to be 0, which means alpha minus beta Ei is going to be ln Ni by n, which means Ni by n is e to the power alpha minus beta Ei, which is by the product rule it will be e to the power alpha into e to the power minus beta Ei. Let us call the equation 2. Now, let us take sum of both the sides. So, sum of Ni by n over all i's is sum of e to the power alpha e to the power minus beta Ei. So, sum of Ni by n you know equal to 1, e to the power alpha is a constant, it will come out e to the power minus beta Ei. Now, taking on the other side we get sum of e to the power minus beta Ei is e to the power minus alpha. Let us call that equation 3. Now, let us put equation 3 in equation 2. So, Ni by n is equal to e to the power alpha e to the power minus beta Ei, and e to the power alpha, or okay, let us write one more step, e to the power minus alpha, because alpha becomes minus alpha, and we know that e to the power minus alpha is this one. So, put equation 3 in that and we get e to the power minus beta Ei by sum over e to the power minus beta Ei. So, you know Ni by n is the probability. So, the probability of being in the I state depends on the energy of that particular state, whereas this one is nothing but constant. So, we get Ni by n as A into e to the power minus beta Ei. Remember this expression when we calculate the statistics from Maxwell-Boltzmann. Here A is nothing but 1 by sum over e to the power minus beta Ei, which is nothing but a normalization constant. So, this is the Maxwell-Boltzmann distribution that we got from the statistics that we use by putting particle in the labels. Now, here for very general systems, what you can see is that the most probable distribution with the total number of particles being fixed and total number total energy being fixed will give us this distribution no matter how the energy levels are, which means that high energy levels will have lesser number of particles and low energy levels will have more particles and will follow an exponential distributions. If you increase the, so now beta is can be shown to be inverse of temperature. So, as I said before that it is nothing but e to the power minus Ei by kBT, k is called Boltzmann constant. So, if T is larger, then what is going to happen is that at higher and higher T, then this quantity becomes smaller and the distributions can get more and more flatter. For example, let us say there is this particular distribution at some temperature. If the temperature increases, then what is going to happen is that 1 by kBT becomes if it is increasing, it becomes even smaller. So, the decay rate will be even smaller and then eventually it can be even smaller, and for different energy levels your probability distribution can become more and more equal when the temperature becomes higher and higher. So, now coming back to this, so we have seen that Ni by Ni is proportional to the power minus Ei by kBT and there is a normalization constant. So, number of particles in any level depends on energy and temperature, and at very high temperature all states will be more or less equally populated. At very low temperature only ground state will be populated, and that is very important conclusion from this particular Maxwell-Boltzmann statistics. If all states are of same energy, then also all states will be equally populated. That also we have seen even before we did that. Even Maxwell-Boltzmann distribution also says that if all Ei's are same, then Ni by Nj will be equal for all of them. Only because they are different, that is why, so it is proportional to the energy. So, if the energy is same, and the temperature is same, then all of them will be equally populated. So, this one irrespective of how the energy spacings is, whether they are equally spaced or the unequally spaced, or whether they are degenerate, all of that possibility can simply come from this particular equation, that it shows that if they are equal energy, then they will be equally populated, if they are separated, then they will be differently populated, and with the increasing energy there will be less and less number of particles at higher and higher level, and with increasing temperature more and more particle will fill up the higher levels.